Hi there, and welcome to this lesson on Pure Mathematics 1. And in this lesson, we'll be looking at an introduction to radians. Now, radians are a measure of the size of an angle. But the most commonly used units, the ones that you'll be most familiar with for measuring the size of an angle, are degrees, where there are 360 degrees in one complete turn. But where do degrees come from, and why are there 360 degrees in a complete turn? The truth is, any number could have been chosen instead of 360, but 360 was chosen because it is a very special number. It's called a highly composite number or a superabundant number. Now, both of those terms mean is that it's a record holder for the number of factors it has for the size of the number. 360 is exactly divisible by 1, 2, 3, 4, 5, 6, and all of those numbers up to 360. And in the world before calculators and computers, that was very useful because it meant a half of a turn was exactly 180, a third of a turn exactly 120, a quarter of a turn exactly 90, and so on and so on and so on. There were many, many fractions of 360 degrees that you could find, which would give you a whole number for the answer. In fact, 360 is so special, it's actually got a couple of other names. It's called a superior highly composite number, and it's called a colossally abundant number. Now, both of those terms refer to the number of factors it has, given the size of the number. But what about radians? What are radians, and where do they come from? Well, radians are the only absolute measure of the size of an angle that is commonly used. 360 was not absolute. It was an arbitrary number chosen just because it was such a useful number, such a helpful number to use. Radians are absolute. Now, in what sense are they absolute? Well, they're derived from the circular equivalent of an equilateral triangle. So if you had a circle and it's got radius r, and you set this angle at O to be such that the arc length from A to B was also r, so that all of these three distances are r. Now, if you do that for any size circle with any radius, then it turns out that this angle here is exactly 1 radian, or it's defined to be exactly 1 radian. Now, how does that compare with degrees? The easiest way to compare it with degrees is to think about what you would have if you had a full circle. So we're going to think about what proportion of a whole circle we have here. First of all, by thinking about the length of this arc compared to the whole perimeter, which would be r out of 2 pi r. 2 pi r is the whole circumference of a circle. Now that fraction or that ratio will be exactly the same as if we had 1 radian, the angle here, out of the whole angle in a circle, 1 complete turn. So those two proportions must be the same. R divided by the whole circumference must equal the same as 1 radian divided by the whole angle at the center. Rearranging that gives us 1 turn, 1 complete turn is equal to 1 times 2 pi r over r. Tidying it up gives us that. Cancelling the r's gives us 1 complete turn is 2 pi radians. Well, 1 complete turn is also 360 degrees. So that means that 360 degrees is exactly the same as 2 pi radians. Or if we halve both of those, 180 degrees is exactly the same as pi radians. And those you should learn. So either learn one of them or learn both of them. Now, rearranging that last one gives us that 1 degree is equal to pi divided by 180 radians, or rearranging it the other way around gives us 1 radian is equal to 180 divided by pi degrees. And it's these two formulas that you use to convert degrees to radians or to convert radians to degrees. So as we said, 1 degree is pi over 180 radians. Well, that means to convert degrees to radians, you have to multiply whatever the angle is by pi over 180. That'll give you the angle in radians. To convert back the other way from radians to degrees, you'd use that 1 radian is 180 divided by pi degrees. And so to convert from radians to degrees, you have to multiply by 180 divided by pi. Okay, I'll let you have a go at working out what that means in practice. So 2 questions for you to have a go at. First of all, try and convert pi by 12 radians into degrees, and then try and convert 300 degrees into radians. So as I say, have a go, pause the video, and come back to me again when you're ready. Okay, let's have a look at these. So first of all, converting radians to degrees. Well, to convert radians to degrees, we have to multiply by 180 over pi. So we'll get pi over 12 times by 180 over pi. Now we could just cancel the pi straight away. So you've got 180 divided by 12, which gives you 15 degrees. So pi by 12 radians is 15 degrees. Converting back the other way, converting degrees to radians. Well, to convert degrees to radians, we need to multiply by pi over 180. So that'll give us 300 times by pi over 180, which gives us 5 pi by 3 radians. Now, don't change radians into decimals unless you have to, and frequently you do have to. The 2 examples we did were chosen because they're nice angles in radians as well as degrees. But if it's possible to write the answer in terms of pi, it is better to do so. But if it's not possible, then you would write this as a decimal. A little bit on notation. You know how degrees are written with a little circle that means degrees. With radians, you've got 3 options. You can write 1.35 and you can write the whole word radians if you want to. Quite frequently, that is abbreviated to RAD. That would mean 1.35 radians. And rather like the little circle, which is the symbol for degrees, a little letter C is used for radians. The C stands for circular measure. So 1.35 with a little c above it also means 1.35 radians. There are certain specific angles that you do need to learn. 360 degrees, as we've already said, is exactly 2 pi radians. You should learn that. 180 degrees is pi radians. 90 degrees will be pi by 2 radians. 45 degrees, pi by 4 radians. 30 degrees is pi by 6 radians. And 60 degrees is pi by 3 radians. These angles turn up very, very frequently in questions. And whilst it's easy to work them out from 360 degrees is 2 pi, it is helpful if you just know them, if you can remember them. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 135 and have a go at exercise 7a. Thank you very much for listening, and cheerio.